Okay, so I was having a misunderstanding with my calculator. So when I put this in, what was happening is that it was understanding that the divide by 4 was on the outside of the cube root. And so when I put parentheses around this whole thing, that took care of it. So was it 2.3 times 10 to the minus 6? Thanks for catching that. Any other questions? So this one's a little different. Calculate KSP from the molar solubility. Molar solubility of silver bromide in pure water is 7.3 times 10 to the minus 7 molar. Calculate KSP. Well, I'm going to start this in a very similar way. I'm going to look at the equilibrium for dissolving silver bromide. So initially I've got none of either of these. This molar solubility is telling me the equilibrium concentration of silver ion is going to be equal to 7.3 times 10 to the minus 7. So the change here, this would be plus S and plus S. You have to be careful because if you've got a 2 or a 3 in here, then this isn't S. It's 3S or something. But since, let's do it this way. So that's 7.3 times 10 to the minus 7. This is also 7.3 times 10 to the minus 7. KSP equals silver concentration times bromide concentration. 7.3 times 10 to the minus 7 squared. Five point 3 times 10 to the minus 13. Any questions? Some of your faces are just so priceless. You're just like kind of disgusted with this. You're like, yeah. Yes. Why can we assume that this is the concentration of silver and bromide? So let's think of if we're trying to calculate the molar solubility given KSP. We would set up our ice table like this, right? I left the C out. Starting with 0 of each, this is going to change by plus S, and that's going to change by plus S. So at equilibrium, the concentrations will be the molar solubility. Okay? Since we're told what the molar solubility is, then we can just use that to calculate KSP.
So the molar solubility is the constant?
Yeah.
When comparing?
The way it works out is when you write this equilibrium expression, anything that has a coefficient of 1, its concentration will be equal to the molar solubility. If it's got a coefficient of 2, it's going to be twice the molar solubility.
So it would be like 2 times.
Mm-hmm.
We can still assume that's the molar solubility just with that.
Yeah, we just have to be careful. here it is the same.
Well, like, so molar solubility is the S, right? If it
Yes.
was 2 in front, it would be like
2S.
So, like 2S isn't molar solubility.
Correct.
Wow.
2S would be the concentration, but not the molar solubility. You don't. You don't. I'm just showing you how you would think it through. Yeah, if it's just one of each, then KSP equals the molar solubility squared. But if we've got like that iron hydroxide where we had 2 hydroxides, we just need to be a little careful. So molar solubility and KSP are related, but you can't just use KSP to compare relative solubilities of 2 compounds, because it's a little more complicated than that. So if we compare magnesium hydroxide and iron carbonate, magnesium hydroxide has a smaller KSP, 10 to the minus 13. Iron carbonate is 10 to the minus 3. And yet, the magnesium hydroxide has a higher molar solubility. And that's because of the stoichiometry. When this one dissolves, you get 1 of each, and so KSP is equal to the molar solubility squared. Magnesium hydroxide, you get 1 magnesium and 2 hydroxides, so KSP is equal to 4 times the molar solubility cubed. We did questions like both of those. So the relationship depends on stoichiometry. If we compare 2 compounds with the same number of ions, this one has 3 ions, 2 hydroxides and a magnesium. This one has 1 calcium, 2 fluorides. And here, if we look at the relative KSPs, this is a smaller KSP, smaller solubility. Larger KSP, larger solubility. But we have to be careful. You can't just use that as a comparison. You have to make sure the stoichiometry is the same.